Hey everyone, I hope you're doing well. I hope you're staying healthy out there. My research project was over nuclear power plants, and without further ado, let's get into it. We got to start with the history, just like most things. We got to talk about the discovery of fission, the first self-sustaining chain reaction, and the nuclear reactor. Fun stuff. So, the discovery of fission. Basically, this man, Enrico Fermi, he discovered that whenever you took an atom, you threw a neutron into the nucleus of that atom, it would split apart and you would have a resulting less mass. Well, he couldn't figure out why, and later scientists applied E equals mc squared to this whole situation and figured out that it is because of a loss of energy. So that's what fission is. It's a loss of energy from the splitting of an atom. So, pretty cool stuff. Pretty cool stuff. Yeah, so the first self sustaining chain reaction. In order to talk about this, we need to clarify a couple of things. First, what is a chain reaction? Well, a chain reaction is whenever you have basically one atom and you shoot a neutron into that. That atom splits apart, throws out some energy, throws out some more neutrons. The atoms around it get hit and split apart. Atoms around those get hit, split apart. You get the picture. It gets big. And then what is critical mass? Well, critical mass is basically the least amount necessary for a chain reaction. And by amount, we're talking about isotopes or atoms, right? And then let's talk about one of the most common isotopes used for nuclear power plants, for nuclear energy. That's uranium 235. Uranium 235 is actually an isotope of uranium itself, which is 238 protons and neutrons. Uranium 235 just has 3 less neutrons. It splits apart easy. On December the 2nd, 1942, Chicago Pile 1 was initiated. So this was a nuclear reactor created by Fermi and a couple of other scientists, and they had created the first self-sustaining chain reaction, which brought us into the nuclear age that we're in right now. So it's pretty cool. Now let's talk about the nuclear reactor. So the nuclear reactor is basically fission at a controlled rate. There's a moderator, there are control rods, there's a coolant, and typically the moderator and the coolant are water. But yeah. Anyways, let's talk a little bit about that. So the moderator is inside the reactor vessel, as you can see on there on the left, and it basically tries to keep the neutrons from getting to crazy high speeds, to keep them at manageable speeds. The control rods are designed to absorb many of the neutrons so that we can have that fission at a controlled rate. And then the coolant is obviously to keep everything cool because it gets very hot, because as we know, energy is heat is energy being put off, right? Or, yeah. Anyways, yeah, so different reactors. Let's look at those. We have pressurized water reactors, we have boiling water reactors, and we have high temperature gas cooled reactors. So these are 3 cool reactors, and the cool thing about them is that they're the most common, right? They're the most used, the most efficient that we have for us right now. And yeah, so let's get into them. There's actually tons of reactors, but these are the 3 most common. So pressurized water reactors, yeah. So there's the moderator and the coolant inside the system is just water. And so what happens is, and as you can see, it's the same picture, right? So what happens is inside there's a pressurized system. That's the very left side. That keeps the water from boiling. Because as we know, the higher the pressure, the higher the boil temperature that there needs to be. So that water is not boiling. It conserves its energy. It sends it off into the next vat of water, the next system of water, which is the steam system. That steam generator basically gets that steam. The turbine turns, mechanical energy produces electrical energy through the generator, and then bam, we got our lights, right? So, and then the whole system resets with the cooling, the condenser where it cools down. But the cool thing about that pressurized part is that it's up to 150 times the normal atmospheric pressure, which is absolutely mind-blowing. It's crazy. That's a crazy pressure to keep it from boiling over. That's because of crazy temperatures. It gets very hot in those chain reaction things. But now we have boiling water reactors. These are practically the same thing. BWRs, they're pretty much the same thing as PWRs. They just don't have that pressurized system, which actually makes it less efficient because you're losing some energy to heat. But yeah, so it turns straight into steam and goes through the system. Pretty easy, pretty cool. Next, we have high temperature gas cooled reactors. So this one is similar as well to the other two. This is how many reactors work, is this kind of system. Yeah, so the gas coolant, the gas is the coolant in the system, and typically is moderated by carbon. That's what the system is moderated by. So it's actually more efficient. It's actually much more efficient. It works well as far as energy production goes. But it's less efficient as far as cooling goes, so it's less stable. It actually doesn't produce as much energy, even though I said it's more efficient. But yeah, because of that cooling factor, because gas cannot cool as well as water. So fun fact. But yeah, good stuff. So now that we've talked about some of the reactors, and as you can see, they're very similar. That's basically how a typical reactor works. We talked about how it works through the chain reactions that happen inside of the reactor, which is through fission from isotopes being slammed into by neutrons. Now we need to talk about the problems, I guess. So the problems is that there are many safety and waste concerns to nuclear power plants, and real costs are high too. So basically what I'm saying is that in 1996, the percentage of power created in the world by nuclear power plants was only 18%, and that was the height of its power, if you take my pun. In 2015, it was 11%. Like, it's been going down. People do not trust it as much anymore. Why is that? Well, it's because of these costs. Nuclear meltdowns, safety costs, extreme half-lives, and waste issues. So let's first talk about nuclear meltdowns. I mean, that's what we gotta stay away from. But it's happened before, Chernobyl, and many other instances, such as in Japan and such. But basically, it's whenever the nuclear material inside is not properly cooled. Maybe a pipe burst and the water didn't properly get to it. It wasn't properly cooled. The nuclear material inside melted down, turned into radioactive vapor, and that vapor then somehow got out, and it just decimates the environment. Absolutely decimates, as we saw in Chernobyl. Miles and miles of land get destroyed because it's vapor, and it carries with the weather, right? So not good stuff. A lot of the public distrust it now because of that and all that. But then there's a safety cost. So in order to try to contain that and make sure that never happens, one, the reactor itself is just made out of pure steel, out of heavy metals and materials. So that's already super expensive by itself. And then there's, of course, the building, which has to be very, very thick concrete and steel wall to contain everything. Once again, high costs. Another reason why we don't use them anymore, or don't use them very much. But we do have some in Arkansas. But then there's also the extreme half-lives and the waste issues that are revolving around this. So this is probably the major issue, is the extreme half-lives. So a single atom of U-235 will take 700 million years to decay for the half-life. That's the half-life, is 700 million years. That's crazy. So if you don't know, half-life is basically how long it takes for a substance, or in this case an atom, to not be radioactive anymore, to decay, to be safe for the environment. That is a long time of isolation from the rest of the world. If we were to rely on nuclear power, then we would have to find a place to store all of this stuff for 700 million years, if not more, if not just a little bit less, not very much less. that's a huge waste issue, a huge issue for just storing, um, and that's another reason why we don't use them very much anymore. But they are still fascinating. Atomic power is crazy cool, and it's created horrible weapons, but at the same time, um, created a vast amounts of energy, and it's still something that we can use today, and I hope become something viable for the future. But that's nuclear power plants. Y'all, I hope you're, once again, I hope you're staying safe. I hope you're staying healthy. The rest of the semester, man, we got this. We can do this. Thank y'all for listening. I hope I'll be ready to listen to y'all stuff, and I hope y'all have an amazing rest of your semester. We'll see y'all.